So our next speaker is Francis Bach from INRIA and ENSR.
ENS. Okay, thank you. So today I'm going to talk about structure sparsity. So there are many of different definitions of that. So in that talk, I will focus mostly on situations where I want to estimate a sparse vectors, okay, a sparse vector, but I want zeros to organize in some way. Okay, so in other words, I don't want to be invariant by permutation. I want to impose some structure. And this has been looked at in many cases, and in particular the group case is well known. So if you want to estimate variables which are organized in groups, then the group lasso or group penalty are used for this. In this talk, I want to do this very systematically. Give me some prior knowledge into your data. I will construct a norm to do so. So this will be the outline of my talk. So I will first provide some introduction to review a bit the notations. And the main theme, of course, if I want to build new norms, is to go beyond the L1 norm. And this will take me 2/3 of the talk. And this corresponds mostly to situations where you want to do supervised learning. And I will also spend 1/3 of the talk dealing with unsupervised learning. Okay, you want to learn some new representations in a similar way that John was presenting earlier today. Okay, so first part, structured sparsity, you want to create some zeros. Second part, I will look at matrix factorizations. So a bit of notations first. I'm going to consider supervised learning, where I have some data xi in RP and some response yi, and I want to predict y from x. And I'm going to consider the regularized risk minimization when I want to minimize convex data fitting term. So in this talk, least squares for simplicity, and also add a penalizer omega. And I'm going to consider sparsity. So this has been studied a lot by people in the room. And there are many reasons to do so. There are several names, basis pursuit, lasso. And this is typically used for two reasons. So the first one is interpretability. So in a sense, sparsity is a proxy for interpretation. You can just simply look at the features which were used for your prediction. And this is often important in practice. And I will focus a lot on that in this talk. And also, you can do high-dimensional inference. So P can be larger than n as long as log P is less than n. So this, you can also do unsupervised learning with similar techniques. This is essentially dictionary learning as was presented by John. So you assume that you have different responses, okay, k responses, or k set of signals. And if you know your design matrix X or your dictionary, then you might want to decompose all of your responses using that dictionary. So this will be when the dictionary is given. But you can also estimate the dictionary, okay, X, and this corresponds to minimizing both with respect to X and to W, okay? So it's often seen in the context of signal processing. X is a dictionary, and you want to find a dictionary X so that if you decompose all of your signals using that dictionary, you get sparse solutions. Okay, so here, omega typically is the L1 norm, and you put an L2 penalty on the problem on dictionary elements. You don't want to import any structure on dictionary elements. And this is often called dictionary learning, and this has been done by several people already. One thing I want to really mention is that dictionary learning is simply the transpose of sparse PCA. Okay, so typically in sparse PCA, you want to put sparse dictionary elements and don't put any structure in the coefficients. But essentially, those are the two same problem. Okay, so why do you want to pose some additional structure? So the first reason to me is the interpretability. So let's look at a simple example. Okay, let's say you want to do a sparse PCA on faces. So let's say you have like a bunch of faces like here, like 1,000 faces, and you do sparse PCA. So you want to decompose every new face with some dictionary elements, and you want to put some sparsity on that dictionary element. This is what you obtain on the right. So here, gray is 0, and black and white are large or non-zero values. And just to help you out, those basis vectors are super sparse. Okay, so here in green, okay, at least in green on the screen, you get the set of zeros. Okay, so it is a situation where you have a lot of zeros, but this does not mean that you can really interpret the result in a simple way. Okay? So here, in that setup, what we will try to do is to use the structure of the problem. So here you have a 2D problem, and ideally you would like your non-zeros to appear in some localized way. And this is what we're going to do by just changing one term, okay, in the formulation, replacing the L1 norm by something else. The goal is to get something like this, where now the non-zeros are convex shapes in the plane. Okay, so the main theme of the talk is give me some prior knowledge of my problem. How can I build a norm to achieve this? Then this is also important for other reasons. First, stability. So it's well known that the L1 penalty does not lead to stable results in terms of the vector W, and you might want to use extra structure to make this more stable. And of course, if you impose prior knowledge which matches the statistical problem, you should predict better. And this, I won't go too much into it, but there are many reasons why you want to use structured models on top of interpretability. Okay, so there are many types of structure. Okay, so I'm sure there are more than this, but typically there are three main types of structure that people have been working on. Zeros, okay, and you want the zeros to organize in a certain way. I'm going to talk about this. But people have also considered spatial structure in level sets. Okay, this is so-called total variation. And essentially, what I've talked about today can be extended to that case as well, but I won't mention it. And finally, this will be the last part of the talk. You can also not caring so much about zeros, but about factorizing a matrix with a certain structure for all of the factors. And this will be the end of the talk. Okay, so here there are many ways of attacking the problem, many applications which have presented here in vision, neuroimaging, and so on. Of course, you can do this in a non-convex way. Okay, in fact, the first approaches to do this were with greedy methods. Okay, and it works already very well. But in the talk, we will try to design convex formulations. Okay, and this means, in the context of sparsity, try to design a new norm. Okay, so what we will do a lot is to look at norms and their balls. Okay, they are unit balls. So here on the left, you have the L2 norm, no corners. On the middle, you have the L1 norm, so you have a usual L1 norm. And here, this is one example of the group L1, L2 norm, which have a specific set of singularities. So in the goal of today is try to design some norms so that the extreme points and faces match what you want. Okay, so let's look first at what is the L1 norm. Okay, so of course the L1 norm is the sum of absolute values. Okay, this is obvious, but it's also a bit more. Okay, so what you can see the L1 norm as being the best convex approximation of the L0 penalty. Okay, so here just to introduce notations, V will always be my set of predictors, so V1, 1 to P. I call the support of W, so W is a vector. Its support is its set of non-zero components. Essentially, the L0 penalty is simply the cardinality of the support. Okay, so here, if you look in 1D, okay, so if you look in 1D, the L0 penalty has a zero value in 0, and is 1 everywhere else. Okay, so if you want to replace this by a convex function, and you want to be below the L0 penalty, and if you restrict yourself to -1, 1, okay, then essentially you're trying to compute the convex envelope of the L0 penalty, you obtain the L1 norm. Okay, this is very, very well known. Okay, and the goal of today is to show that if you replace cardinality by something else, so you want to put some additional prior knowledge into the problem, and this will be done through a different function than cardinality, then you can do a similar thing, compute the convex relaxation and compute the convex envelope. So this is what I'm going to do. So I'm going to put some assumptions of the problem. We cannot do this for all possible functions. Then we consider a set function, so which goes from subsets, okay, all possible 2 to the p subsets to real numbers. Okay, I will assume it is non-decreasing. Okay, you want to penalize more larger subsets. And I will also assume that it is submodular. Okay, and as I will show, this allows us to do all the things that I've somewhat promised, deriving convex relaxations and being able to derive a unified set of algorithms and analysis. So first, what is submodularity? Okay, so you have several ways of seeing submodularity. So remember, f is a function on subsets, and submodularity means that if you take any two subsets A and B, f of A plus f of B is greater than f of A intersect B plus f of A union B. So if you're an additive measure, you have equality here, and to be submodular, you just need to have one inequality. So a traditional way of seeing an equivalent way of defining submodular functions is just written below. For any, if you isolate any single element k, then the cost of adding k to any set A is decreasing in A. You have this notion of diminishing return, and this is often the easiest way to characterize submodular function. So in a sense, the first intuition about submodular function is the fact that they behave like a concave function. You have diminishing returns, and in fact, if you take a function which is a set function, which depends only on the cardinality, then it is submodular as soon as G is concave. Okay, so you have a nice relationship with concavity, but in terms of behavior and analysis, it behaves more like convex functions. Okay, the main reasons are that you can minimize them in polynomial time, and you have a nice relationship with convexity, which I will describe later. So here, of course, this has been already used quite a bit in signal processing and machine learning, in particular through the total variation, which corresponds to cuts, and also by to do optimal design, because the log det, as I will see, the log det of a submatrix is a submodular function. So what are the classical examples that people have considered? I've already talked about concave functions of cardinality. There is cuts. Okay, if you take a graph, a cut in a graph, so give me a set A. The cut between A and V minus A is a submodular. Entropies, if you take P, any P random variables, and you consider the entropy of the subset of variables indexed by A, it is a submodular. And also, if you take Gaussian random variables, the log det of a submatrix is submodular. You also have network flows. Okay, this is very useful in terms for efficient algorithms, and also rank functions of matroids, but I won't use this at all in the talk. Okay, so why? So there are many ways of seeing submodular functions. The way I like to see them is through the relationship with convexity. Okay, so if you take first any set function f, okay, so essentially you can identify the set of subsets by vertices of the hypercube. Okay, so this is done over there. Any subset, okay, can be mapped to a vertex of the hypercube. So any set function defines a function on the vertices of the hypercube. Given such a function, you can always extend it to the entire hypercube, and this is essentially what the, in fact, Choquet integral is doing, but often the Choquet integral is referred to as a Lovász extension in that setup. So you take any W, okay, so it can be in the hypercube, in fact, in any places in RP. You order its components, okay, this takes n log n or p log p time, and then you define the submodular function, the Lovász extension, as a piecewise linear function like this. Okay, and if you look very carefully, this corresponds to cutting that hypercube in simplices and doing interpolation. Okay, it's not a trivial statement, but this is what's happening. So here, why is it called extension? Because if you are at a vertex of the hypercube, you recover the submodular function. So f of the indicator vector is the value of the function. Okay? So essentially, what we're going to do is see all set functions through the Lovász extension. So why is it so nice? It's because essentially submodularity of the set function is equivalent to convexity of the Lovász extension. This is a nice result by Lovász in the 80s. Okay? On top of that, if you want to minimize the submodular function, okay, so minimize the Lovász extension on the vertices of the hypercube, you can do this by optimizing over the full hypercube. Okay? So this is one of the reasons why you can optimize submodular function in a polynomial time. So I won't do this so much in the talk, but there are a lot of nice links between submodularity and convexity. So let's now go back to our problem. I want to design a new penalty to induce sparsity. And what I want to find a convex approximation of the function f taken at the support. Okay, so the goal is have this function theta, which will be my prior knowledge on my predictors, and I want to derive a convex lower bound, namely the convex envelope. And what you can show is that if the convex envelope of that function is essentially the Lovász extension taken at the absolute values of the components. So just as a safety check, if f is the cardinality, okay, the Lovász extension is just a sum of components, and you recover exactly the earlier result that the L1 norm is the convex envelope of the L0 penalty. Okay, so this is, so now essentially you can, whenever you're dealing with such a function, you can look at the convex envelope. So at the end, all those norms are, since f as the Lovász extension is piecewise affine, all the norms are polyhedral, and all the unit balls are polytopes. Okay, so here I gave an example in 2D. Okay, so it's any submodular function, and if I specialize to some functions, I get back the L1 norm, L infinity norm, and this is a group. This is another norm. So you can show several results on the problem. So I won't give all of them. The first one is the notion of stability. Okay, so set A is stable. Okay, if you increase A to something bigger, you have to increase F as well. So essentially, if you minimize something like this, you will always attain a stable support. Why? Because if you're not stable, you can always add a bit of W. Okay, you can always decrease the loss, but you will not increase the function. Okay, so in a sense, you can only attain stable subsets when you consider this function, which is hard to optimize. And what you can show is that if you replace f by the Lovász extension like this, you preserve that fact. Okay, so one example of some property which is preserved by going from the non-convex formulation to the convex formulation. There are other ones, and I won't talk about too much today. So some further examples. Okay, this is the L1 norm in 3D. Okay, this is the L infinity norm. Okay, you get the then you get norms with many extreme points. And if you look this carefully, you see the L1 L infinity norm. Okay, it's a sum, it's a group norm where you have some norm. You have a group of size 1 and a group of size 2, 3, which is the so-called L1 L infinity norm, which is a subcase of our result, and even more complex norms. So let's look closer at some examples, try to see if we gain anything by looking at all possible submodular functions. So we will do it in two directions. Take existing norms and see them through submodular eyes, and do the opposite. Take a new submodular function and try to see that it does lead to an interesting regularizer. So the first thing I'm going to consider is L1 and L infinity norms, where you consider norms which are sums, okay, over a set of subsets, okay, here H, and I take for all elements of capital H, bold H, I will take W, okay, my vector, restrict it to that group WG, and compute its L infinity norm. So if H is a partition of 1P, this recovers exactly the group L1 and L infinity norm, but you can extend this to situations where you don't have a partition. Okay, this was looked at both by Zhao and Yu, and also by my student Jenatton. And essentially, those norms were first designed in terms of supports. Okay, if you consider the L1 L infinity norm, so the case where H is a partition, this will select groups of variables. Okay, if you select a variable in a group, you will select the entire group. Okay, so the one way of seeing this is as a support, okay, or more the complement of the support will be have to be union of groups. Okay, the reason why because when you minimize this, you will tend to push some of the norms to 0. Okay, so you create some zeros for certain WG, for certain groups G. So at the end, the set of zeros is a union of those groups. So the support is a complement of this. So the support is okay, you get it. Okay. So let's look at some examples. Okay, and okay, so here this corresponds to a submodular function, which will do what? Which will simply take a set A and count the number of groups G which has non-zero intersection. Okay, so if you take the partition, if H is a partition, this gives a very natural interpretation of the L1 L infinity norm, namely that you want only, as soon as you have one variable in the group, it doesn't cost you anything to add a full group. Okay, of course here, the stable sets are exactly the stable sets are exactly what you care about, namely select groups altogether. So here, a key aspect here is that the new formulation allows you to go beyond simply counting subsets. Okay, in fact, our first work on using those norms were only based on what are the patterns which you can attain. This new formulation allows you to have a finer interpretation. You put a prior on all subsets. Okay, some of them will be forbidden, but for all of them you have a cost, and this, and I won't give any too much details, can be used to refine a bit the problem. So let's look at a very simple example. So if you consider variables which are organized in a line, so here 5 variables, and you use as groups all the groups which are in blue here and here. So if you penalize with the norms, with a norm based on that group, you will put to 0 some of the variables in the blue groups. So at the end, if you put any of the blue here and any of the blue here to 0, what you're left with non-zeros are variables which are in a sequence. Okay? The non-zero have to be contiguous. So this you can show, of course, formally, and you can extend to other topology. So now if you, okay, and in fact, what you can show in that setup, that with set of groups, that set of group, the submodular function, so your prior on subsets, is essentially the range of the subset that you select. Okay, so essentially, you put a prior that you want a subset with small range. You can go from 1D to 2D, okay, by considering all rectangles on the right, left, top, and bottom. Again, if you put to 0 any of those groups, what you're left with as non-zero is a rectangle in the middle. So here, of course, you don't know where the rectangle is, and this will be found automatically by the algorithm. From this, you can go to add some more angles, okay, and then you can carve any convex shapes in the plane. And essentially, this is what we have used in the context of a sparse PCA. Okay, so in the context of sparse PCA, we have considered a dictionary learning problem, or PCA problem, when you want to factorize the matrix Y with all your signals as X times W. X will be my dictionary elements, and I want to impose a prior that X will have some structured sparsity in the following sense. I want the non-zero to occur localized. So this will be done by just changing the L1 norm by this group norm. So this is what you obtain with, on the left with sparse PCA. So the zeros are scattered all over the place, and as soon as you impose this localized constraint, then the zeros appear in convex shapes. So here, of course, this is purely subjective. I just say it's beautiful, okay? I think it's beautiful, but in the paper, we have also quantitative evaluations showing that the representations obtained from that dictionary improves for doing face recognition, okay? So it's not only subjective. In fact, those occur, but forget about it. Okay, so this can be used in a similar framework as, yes, Emmanuel? Oh, you mean here? Maybe the top left is really here? Yeah. Okay, so here you ask a very good question. So what I've hidden under the carpet is the fact that you need some weights inside those norms to avoid really penalizing too much the corners. Okay, so in fact, Rodolphe has thought a lot about thought a lot about those weights. And in fact, this interpretation allows you to really be more explicit in what you're doing. So when you have norms, in particular, if you replace the infinity norm by the L2 norms, then there's a lot of overcounting all over the place. And with L infinity norm, this is not the case anymore. And with that interpretation, you can really avoid those painful issues. But it's clearly a problem in practice. You want to avoid that. What you want to make sure, that if there is some signal over there, okay, then you can get it. Okay, if you consider our solution here, this is the case. Okay, so sometimes you want you have signals which is close to the boundary, and you can still get it. But this is indeed somewhat of a problem in practice. So let's forget about this. So this was in a one direction. So we just took existing work and cast it as a problem with submodularity. You can do the opposite. Okay, you can take the list of submodular functions which I have presented earlier and try to see if the norms are interesting. Okay, so one interesting example, and I won't have time to present it, is to look at entropies of subsets. Okay, so if you have your covariance matrix, typically all the norms that people have been designing for sparse recovery do not depend on the design matrix. Okay, so just a function of the weight vector. You can design norms which now depend on the design matrix with the, so here, capital X. And we have shown, and we also have extensions with Edouard Grave and Guillaume Obozinski, where this improves a bit in terms of recovery. So let's look at some unified algorithms and analysis. Okay, so first, all our norms are polyhedral. Okay, so it can be a big LP, but the number of faces and vertices can be quite big, so it won't work. You can design a subgradient easily, okay, because you can design a subgradient of the Lovász extension, but this is still too slow. And what I want to present now is really a nice link between combinatorial optimization and continuous optimization. So for that, I will consider proximal methods. Okay, so these have been already discussed at this workshop. If you want to minimize the sum of a differentiable function, typically a square loss or logistic loss, plus your regularizer, then you can have very efficient algorithms, okay, which are essentially gradient descent, if you can solve those problems efficiently, okay, which is the so-called proximal problem. So when omega is the L1 norm, this is soft thresholding. And it turns out that for all the norms which I'm considering, you can solve that problem efficiently, and it has some nice links with submodular function minimization. Okay, so this is in fact first done by Chambol and Darbon. Okay, so let's consider the proximal problem. Okay, you have a square norm plus lambda times the Lovász extension. So this is a continuous optimization problem. Okay, you want to find W in RP, and what you can show is that if you have the solution of that guy, okay, then you get the solution of all those problems. And those problems are what? You minimize a submodular function f, okay, and of course, small f is a Lovász extension of capital F, plus some modular term, which is just a linear function. So the key thing to notice is that solving this is equivalent to solving that, and of course, vice versa. So this means that if you want to solve that guy, you can do it by a sequence of such submodular function minimization. Okay, and in fact, you can do it by a fixed number of such problems, and this is a divide-and-conquer strategy by Grönveld. So at the end, by simply at most p submodular function minimization problems, you can solve the proximal problem. Okay, so it's really a nice link between convex optimization and combinatorial optimization. So here, of course, it works much faster than subgradient methods. So this is very basic simulations. Since the proximal step is efficient, you can really improve on subgradient. In terms of analysis, okay, so I won't give any details, but you can have a unified analysis of that problem. So essentially, if you know how to deal with L1 norm, and if you know how to deal with L1 L infinity norm, and if you have read a nice paper by Negabam et al., you discover that the only thing that you need to prove anything for sparse recovery or for also estimation guarantees is to be able to decompose the norm, okay, over a piece on the support and a piece outside of the support. It turns out that in our setup, we do have partial decomposability, and this is enough to extend all results of Negabam et al., and the one also of Zhao and Yu. Okay, so I won't give the details because it's a few slides, but at the end, we recover the results of Negabam and Wainwright, which was for the L1 and infinity, but they extend to all possible cases. Okay, so here you have unified analysis, but I won't give too much details. So there are a few caveats to that framework, and the first one, and this really was a big problem for me, is that I don't like L infinity norms. Okay, so I don't like L infinity norms because they have some extra behaviors. So if you take the L infinity norm, okay, so this corresponds to that submodular function. So this is not supposed to have any sparsifying effects. At least when I play around with my submodular function, there's no sparsity involved, but it has some extra corners. Okay? There's no blocking at zeros, but you have some blockings at vectors of equal magnitudes. Okay? So this is typical in infinity norms. Sometimes this is considered as a feature of the method. To me, it's clearly a bug because you add some extra constraints, and if you don't want them, it's not going to work. This is for L1 and infinity. If you consider the group L1, okay, then you have this square is not useful. So this is a one limitation. The other limitation is that we can only deal with submodular functions. And of course, there are many situations where you want to go beyond submodular functions. So Guillaume Obozinski and I have worked on that problem, trying to remove those problems. And I will go quickly on this. And we have simply considered a new norm, okay? So if you know about, it's very classical to express L1 norm as a weighted L2 norm, okay? So if you put F being the sum of components, then this is done to recover the L1 norm, okay? If you minimize over eta, then eta I is simply the absolute value of wi, and you recover the L1 norm. It turns out that you can replace, so this corresponds to the case where F, capital F, is a cardinality, but you can replace cardinality by any submodular function. It also defines a norm, okay? And what you can show is that that norm also has some convex relaxations interpretations. And namely, now you're doing the convex envelope of what? Of not only the support function, but you replace the constraint to be of the L infinity ball by a penalty on the L2 norm. Okay? You try to do both penalizing and constraining the support. And what you can show is that if you want to find the convex envelope of that guy or the homogeneous convex envelope of that guy, you recover exactly that function. Okay? And this you can extend to Q and P different from 2. Okay? You can replace L2 norm by LP norm if you want, but the key setup is the L2 norm. And if you use that norm and you compute the unit balls of those norms, you recover the group L2 in the context of non-overlapping groups, and you also correct some of the problems that were some of the extra corners which were created by the L infinity norm. Okay, so here, so essentially, if you don't like L infinity, and you should be right not to like L infinity, then you can use L2. Okay. How much time do I have left? 10 minutes? I think I will take 10 minutes. Okay. Okay, so this was for Sparse trying to impose some structures on the zeros of your problem. So for the last part of the talk, I have 3 slides. Okay, so it's going to be quick. It's trying to go beyond simply like having certain sets of zeros and try to be as systematic, okay, but for matrix factorizations. So what we're going to consider? We're going to consider for matrix X of size n times d. And what we want to decompose it as a sum of factors. Okay, so the factors, U, M, V, M, we will constrain them to be in certain sets. Okay, so typically, small number of non-zero elements belonging to 0, 1, or positivity. Okay, any possible set, it might not be convex. You can deal with anything. Okay, so here the goal is, give me X, I want to recover somewhat a singular value decomposition, but now I want to put the constraints on U and V. Okay, so we have different types of constraints, and here this corresponds to a lot of unsupervised learning problems. If you take k-means, what is k-means? K-means essentially, so this is clustering, this corresponds to U being only zeros and ones. Okay? Non-negative matrix factorization, this corresponds to U and V being non-negative. Okay, so you have many unsupervised learning problems which can be cast as that problem. Oh, sorry. So here, just to restrict a bit the problem, I will consider only cases for the talk that U and V are unit balls. Okay, so I will not consider positivity, just consider belonging to a unit ball, L1, L2, and so on. Okay, so now I will define a norm X. Okay, so I will define the norm theta on X, which will be the infimum over all possible decompositions of X as a product of factors UM, VM of the norms of those factors. Okay, so this essentially you want to, among all possible decompositions, you want the one with the smallest norms for their factors. So this, first, there are several properties which you can show. First, the rank can be always chosen to be less than ND, simple Kara-Theodori argument. Theta is a norm, and in fact, it's not a new norm. So in fact, I've worked on that with Julien Mairal and Jean Ponce like 5 years ago. Okay, so that reference. And we were very happy about this, but it was already done. Okay, that's why we gave up for a few years. So why is it already done? Because if you look at the dual norm, theta y, okay, this one, then simply the matrix norm. It's a supremum over u times y times v over u and v in unit balls of some norms. So essentially, what we were considering, okay, to do matrix decomposition is simply the dual norm of an existing norm, and even worse, this already has a name. It's called summing norms, okay, by James Sons. And in fact, this dates back to this, Joel Trop told me this. It dates back to Grothendieck in the 50s or 60s, I don't know. So at the end, this is all very old. And it's also an instance of an atomic norm. I think the next talk by Ben Wright will cover this. It corresponds also to an atomic norm. Okay? So let's look at some special cases, because it's a nice norm, but it turns out we can never compute it. So second source of big disappointment is already done, plus you can't compute it, except in 2 cases, when one of the norms is the L1 norm, okay, so then you get back a group L1 norm. It's not super useful. There's no decomposition in that setup. And of course, if you have the 2 norms being the L2 norm, you break over the nuclear norm, which is well known. Okay, so on top of those 2 cases and a few others, which are a bit more complicated, I don't know any possibility, I don't know any closed form expressions. Okay, so what we're going to do is quickly find some relaxations, okay, for either theta or its dual norm. And of course, and this is the only novelty in what I'm presenting, not only you want to relax the value, okay, upper bound and lower bound, you want to be able to recover decompositions. Okay, you really want, give me matrix X, give me factors U and V. So in terms of relaxation, so we're going to use very standard semi-definite relaxations. So I will take the case where we have the L2 norm, because it's much simpler. Then I can consider the dual norm. Okay, it's a max over U, which is my set of factors U, times a max over the L2 norm, and you can maximize in closed form with respect to V, and you get the maximum of a quadratic function of U. And of course, as always, you're going to relax it by considering the set of UU transpose, which I call capital U, and then you can design a lot of relaxations of that set UU transpose. Okay, for example, there are 2 different sets which you can use with certain guarantees. Okay, so the goal is not to go too much into the details. You can design semi-definite relaxations for all of those norms, okay? Some with constant factors, and this were first done by Nesterov and Grothendieck in the 40s, and also in some which, in other cases as well. But what I want to really insist on is that it's not sufficient to be able to compute an upper bound on the dual norm. You want to be able to recover the decomposition. And this you can do by a certain form of conditional gradient algorithm, okay? Essentially, you can recast the problem as what? I have a bunch of vectors, xi. Okay, this will be, essentially, xi will be my matrix, x will be a matrix, and xi will be the factors ui times vi transpose. And you want to approximate a vector x as a combination of those elements with the minimal possible L1 norm and the constraint on positivity. Okay, so this is what you need to solve, but the catch is that I might be infinite. I is very large. You're not allowed to do Fista. Why? Because you cannot represent your entire weight vector alpha. And what you can only do is you can access only your families of vectors only by maximizing linear functions, okay, on those vectors. Okay, so this corresponds in my setup to maximizing the dual norm, to computing the dual norm. And it turns out that, and this has been done also by other colleagues, that if you only know something like this, okay, you can recover your decomposition, okay, using a form of greedy algorithm. Okay, this is really related to the greedy algorithm. And if you want to know more, you can come and talk to me after the talk. So to conclude, so I presented 2 sets of work. One which is based on trying to impose some structures on zeros and trying to do it in a systematic way, okay? And this was done through submodularity. So there are, of course, a lot of things which are missing, and to me, the most important to me is how you should find that function, okay? So this relates to the question of Emmanuel. There are a lot of hyperparameters when you start to deal with those problems, and you want to estimate those directly from data, and this is clearly an important problem. As well, for the matrix decompositions, there is one aspect, I think, which is a bit disappointing. Okay, it is a general convex framework, so it's nice and convex, not computable, okay, but you can have the relaxations. But really, the most troubling aspect is that empirically, in all my experiments, it has not been able to beat existing simpler methods. So the method that John was referring to, alternating optimization, okay, you want to factorize x in U times V transpose. So when U is fixed, it's a convex problem in V, and vice versa. So just alternate between U and V. This has no guarantees whatsoever, but this behaves surprisingly well. And my hope by doing this was to be able to get guarantees, but it's been a failure for the last 5 years now. Okay? But I'm still hopeful. Okay? And last point, I think there is nice work. I think the original work on atomic norms by Chandrasekaran, Recht, and others was considering recovery guarantees, but if I understand well, this was for not all possible matrices, okay, for rank one factors in particular. So here the goal is to take the problem of John, which is about to do dictionary learning, which corresponds to 2 factors, one sparse, one non-sparse, and I want to make sure that I recover it. So this is not the case for the moment. And methods not based on like convex optimization have been able to prove some results. And the hope is to be able to do so also with those convex relaxations. Thank you for your attention.
Somehow, images, you kind of know what you want, but in general, data, they're supported by
Sure.
So you have some recommend between what we completely support.
Yeah, so I guess the question was, is there any relationships between the design matrix and the norm? And I have to say, this is, to me, a troubling aspect, is that so you have 3 aspects to a problem when you play with sparsity. You have the design matrix, the support, and a third which I've forgotten, but it's very important. And typically, when you prove results, you want to adapt the results to the combination of a design matrix and a weight vector. And here, so if you don't do this, results by using some, like structured sparsity are not better than L1. If you're not willing, if X is still invariant by permutation and obtained by the just random selection from the Gaussian ensemble, this will not help a lot. Okay, so the key aspect is trying to design the analysis for specific dictionaries. Like for images, X is not round NP. Typically, X has some structure, and we want to use it. But for the moment, we can't do it.